Cool. So there's going to be an announcement that's going to be sent to you in about like 5 minutes. And this is something that happens to me a lot. Basically, it's going to show you a way that generative AI fails. Actually, that is something that's very primitive, very simple. Like, you'll be surprised about how it cannot get this one thing right. And I wanted you to, that was going to be, like, I was going to actually use this to come up with some quiz questions, a good number of them actually. That's one of the reasons why I think it's kind of fun to use the AI for that reason, generate questions. But I thought this is more valuable for us to sort of understand what went on. And I do want to do more of this because I think there's the sense that like career prospects have been kind of like made much more morbid. This damn thing is actually doing a lot of things that we used to. And I really want to emphasize the ways the machine fails, because that shows that we are important, we matter, and our professional competencies matter. So I think it's going to be good for us to look at these things when we actually encounter them. There will also be a few questions that I'm going to ask you to complete on your own. But ordinarily I would actually have them right now, but when I was talking to Toby, and I think all of you know who Toby is, he teaches CS1, CS2. So he actually depends on finite state machines in specifically 2 cases. One of them is software engineering when he teaches it, especially user interface design. And the second one is game design. And so it's going to be fun for us to actually get a few problems that he can generate in those contexts, and then I'm going to ask you to work on, because that would mean that this is like, I actually like math for the sake of math, but it's not enough to sell it. So I think this is going to be a good way to show that what we are learning has lots of interesting applications. Yeah, so let's actually start with some things so that people are really kind of like, well actually, it is in 2 minutes you will get that announcement, and maybe we should actually start by looking at it. So one of the things that I was looking for was to have like a good set of these questions, multiple choice. I might actually even expedite the sending of it. Or I should do it this way. I should share it with you on the screen here. If I can find it. Okay. Check this out. I shared this particular chat with you, so you'll get like a transcript also. So I need a multiple choice quiz question on finite state machines. Theme of the question should be, what kind of numbers does the following finite state machine accept? So for instance, it could have been, these are all the binary numbers that start with 0, that sort of thing. The alphabet should be 0, 1. There should be 5 choices with 1 and only 1 correct answer. Now, I learned to say this because I actually had in the past, when you actually make it generate multiple choice questions, it gives you questions with multiple correct answers. So it's a machine, you really have to say what you want. Pause for a second. Here's one multiple choice question you could see. Okay, could you also draw this on the whiteboards next to you? So this is the state machine that we're getting. So you have state A, state B, and then, so go ahead, do that, and then you tell me like what you think it's going to be, and we'll see if the choices actually match up with it. And when you think you know the language of it, so when someone says, here's, if I may have just your attention, because I like the fact that you're all busy. So just want to say one thing. So when someone gives you a finite state machine and you figure out that there's going to be certain inputs that leads to an accepting state and certain inputs that leads to a rejecting state, the language of that finite state machine is the set of all the strings that take you to an accepting state. So here, what I want you to do is like, what is the language accepted by this finite state machine? So you can say something like, oh, these are all the binary numbers that start with a 0 or end with a 1, something like that. So once you do this, tell me what the language of the finite state machine is. And B is the only one that I should have double circle, and I see some of you, all of you maybe. So you should double circle B. So if an input takes you to state B, that means that whatever string that took you to state B is one of the words accepted by it, but then the language is like all of the words that are accepted. Yeah?
I know the answer.
Go ahead.
As long as it ends in 1.
As long as it ends with 1. Did everyone come up with that conclusion? So, okay, that's good. So then, all binary numbers that end with 1. So C is the correct answer. And then I said, this is the right format, but please make it a little bit more challenging because I have good students and they pay a lot of money to come to IC. I'm not going to waste their time with this simple stuff. So it gave me this. Go ahead and do this one. All those things that I said about you was like in my mind, and it read my mind. So.
Sure, yeah,
I should do this. A, B, C, and D. C is the only accepting state. C.
I think you could just at some point do 0, 1, 0. Like it doesn't need to end in 0, 1, 0. Oh, C is the accepting state?
Yeah, C is the accepting state.
Oh, that's it.
So B goes to A on 0, B goes to C on 1. For C, 0 takes you here.
So you need to end with 0, 1, 0.
And 1 takes you back
0,
to
1.
And then D, so you stay in D. 0, 1. Okay.
So you cannot say 0, 1, 0. You must say 0, 1 at some point.
Yeah, so do you have an answer? Actually, let me go with someone else. Does anyone have a sense of what the language of this finite state machine is? You have one?
Yeah, I figure out like one.
Can I hear it?
No. Oh yeah, I just take 0, 1, 0 sequentially, because then you can't get to the accepted state. Because you just stay in a rejected state.
Yeah, so if it's 0, 1, 0, gets you in trouble.
Yeah.
Sure. Okay. What was that?
It can't have a 0.
I think that the 0, 1, 0, so 0, 1, 0 takes you here, and there's not. And there might be other 0, 1, 0 cases, right? Yeah, right, like this one particular thing. Yeah, not always, but in some cases, yeah. Does anyone have a sense of what this machine is accepting? So one thing that the only thing that I heard so far was that there are some cases, not all, there are some cases where a 0, 1, 0 will get you in a place where it's not accepted. But then there are other ways you could encounter that pattern and it is accepting. Like 0, 1, how was it?
If you're on D and you get a 0, 1, 0, then you're fine.
Yeah, but because, yeah, that's right, it doesn't immediately rule you out, that's right, yeah. Does anyone have a more complete sense of what the string is? Yeah.
If at any point you have a 0, 1, well, okay. If you are on A and you say 0, 1, you get to C. If you're on B and you say 0, 1, 0, 1, you get to C. So you need a 0, 1 to get to C.
So it should have a 0, 1.
Yeah.
accepted word should have a 0, 1 in
Yes.
it. Okay. You know, something like that is like, that would be the language of this, assuming that you're correct. D is the correct answer. So let's see, what are the options? All binary numbers with an odd number of zeros. I'm not buying that. So all binary numbers that end with a 0, 1. I think there's the 0, 1 thing that you mentioned, but I don't think it's the way they said it. All binary numbers that contain the substring 0, 1 exactly once. So I actually thought that this has promise, but then just exactly once is, I don't know how they reinforced. I don't see that here. All binary numbers with an even number of zeros followed by a final 1. That's weird, actually. All binary numbers that begin with 0 and end with 1. And the correct answer is D.
Yeah, that makes sense.
Really?
Yeah.
I found one with an odd number, because if it's 3, and you goes 0, or like, oh, never mind, that's even number of zeros followed. So is that even number of zeros total, or even number of 0 ones?
Zeros.
Even
Yeah,
number
if you
of
have-
zeros.
If you have 3 zeros, it goes from A to B, B to A to B, B to C. If you have 0, 0, 0, 1.
So that's wrong.
Oh.
Yeah.
Right.
So it needs to be.
Watch this. Are you sure about this one? That it is indeed D.
Oh.
But then the answer that it gave, I think, is also wrong. The next one. So I have this happened literally before class started. So I don't know if its second answer was right or wrong. But when I saw that, I said, like, this is unacceptable, because this thing right now. So I heard this other news that apparently one of the famous ones, I forget which one, was able to find a math error in a very long physics paper that was published that has some significant, like, foundational results. And it turns out to be the case. Like, the math in that physics paper that was taken as God's word was actually wrong. Like, there was a problem with it, and the thing found it. And then it fails at this. And this is the paid subscription. I'm not like using some freebie that you could explain that way. This happened a lot when I was teaching computer networks. That in the simplest calculations, like checksums, which is like some basic way to make sure that nothing was broken as it was being transmitted, it constantly gets it wrong. And then you say, like, are you sure? And it figures like, oh yeah, sorry, it never says sorry. It says, like, here's the right answer. It's almost like it's testing me. So I just wanted to make sure that you see this, you witness this, not because I'm saying, hey guys, don't use it, it's plagiarism and it's not real. It's not the point. The point is that if you don't know what you are doing, then this thing is not a reliable assistant. If you know what you are doing, like, I could actually use this to save a lot of time to generate a unique question to every single one of you, because I can just see if it's actually done right, but I don't have to do the typing, so it saves me my time. But if I'm not at the top of my game, this thing actually could sink me. If I'm at the top of my game, this thing actually saves me time. And I want you to constantly keep that in mind. This is not the time to give up on learning, because many people are doing it, and we are doing that for something that is far from perfect. So you have to be good enough to catch it when it makes a mistake, but then also be able to utilize it to be able to do more work in the same amount of time. And I also think that, like, I was talking to Toby about this, this is not so far intelligence, it's actually mimicking behavior. So when it generates a question, it does it based on other cases of generating things. And then when I say, are you sure, it's thus to think about, like, how people correct themselves. So it really has to be guided to do the right thing. And so for that reason, again, this is a potentially useful thing, but unless we are at the top of our game, this is no good. So I wanted to give you one more thing, and then I want to talk to you about the big deal for today, which is the non-determinism aspect of finite state machines. And so here's the thing, and I showed this to you, hopefully you don't remember. Doing it again is going to be very instructive. Suppose that you are designing the finite state machine for a vending machine. Whatever you're buying is worth 40 cents, and not pennies, nickels, dimes, and quarters are the coins you have. And as soon as the amount of money that's placed in is at or exceeding 40 cents, you basically have reached the final state. And then there's this other part, that how do you return the right change, which I'm going to talk about in a second. But I want you to design a finite state machine that actually does this. The thing to be purchased is 40 cents, and the coins that the machine is accepting are nickels, dimes, and quarters. Draw the finite state machine for this thing. 5 minutes, 10 minutes. This is not a trivial one.
4 times 0. So
Oh, by the way, guys, I think it might be important for us to draw the state machine in the same way because then we can compare answers. What I propose is this. So how many states do you think this is going to have? Can anyone guess? How many states do you imagine this machine having?
3.
Did you say 3?
Yeah, minimum of 3 and then.
But if I put like nickels, like I'm moving up to 40 in quite a number of steps, so it's going to be more than 3. So yeah.
I was gonna say 8 or 9, because you need minimum, or the maximum numbers you need is 8 nickels to get to 40 cents.
That's
And
right.
I don't know if you need a state for like the excess.
Yeah, I do think that we actually need this. So like basically there's going to be a starting state. And then there's going to be a state that represents 5 and then 10.
Yeah.
Yeah, keep doing this. Have like 2 columns of the multiples of 5 and put your transitions on those so that we can compare and contrast what we individually come up with.
So we're going by 5.
You missed a good thing. We saw ChatGPT massively fail. Sorry. Yes. And quarters. So yeah, like the next row should, like under 5 should be 15, under 10 should be 20.
Oh, okay.
Yeah.
So yeah, we just.
Actually, Piper, if you do like 5, 10, and then 15, 15, 20, 25, 30, like 2 columns.
Oh. Oh.
Zero's gonna go to 5. That's a negative. That would be negative. And 0 goes 0 here.
Okay, now the zero starts to work. We have a 5. We have 1.
Oh, yeah, yeah,
The
yeah.
answer is 1 of
Wait,
it.
like the zigzag just did there like that.
Oh,
So we just go, we just trace 10 all the way down.
Each of these arrows will have
There's gonna be somebody, I guarantee it. There was somebody who's
And then
5 is gonna go to 10, 5 is gonna go to 15.
So then, well, we could just do this.
Yeah, those are gonna be 9.
And then you can have arrows on the side.
that one's okay, so quarter, we could just do 25 and 25. And we go here. Or we could do actually 25.
25 is good. 5 to 30 is
Or we could do 25 or plus 10, and then we got 35, and then we do another nickel.
But they're just answering. So we need to do something. 25.
You can have a leftover 10.
2 more arrows.
Oh, 15 and 40 is gonna be important.
Yeah.
15 and 40.
Well, so you got.
Oh,
Yeah, so I go 25.
Oh, this is gonna go 5.
no, we do this, and then go Q. Because that means that at this state, it's a quarter.
That's a
That's a quarter.
Yeah, but why do we have this? Are you
Because
saying
they
we're
put a
going
quarter in the
from
vending
this?
machine.
So what do you think? You're gonna do what you're-
Yeah.
If the first coin is a quarter, right?
Yeah.
If the, yeah.
After they pick that up,
I didn't know what you were saying. I thought you said this started from-
Oh, no.
and then goes to-
What would you do? More organized.
Yeah, 5 to 15 is gonna be.
You guys are done?
Yeah.
Okay.
That's gonna go straight. 15 to 45.
So it looks, you guys are done?
Kind of. I guess I just have a question about finite state machines.
Oh, that's-
Sure.
It depends.
Oh, 20
Let me
to
hear your
35 is
question.
gonna be
So
great.
I will either answer you directly or
Oh, wait,
I might need to
No, 10, 10, I don't know why.
I guess I'm just questioning if does this state itself deposit whatever
Oh my God.
excess? So if you could just be like n minus 4 excess or the state of 45, 50, 55.
Okay, wait.
And then that is gonna be excess.
In fact, it actually
Five
makes
to
it
thirty,
so
five
there's
to
a
thirty.
algorithmic component to this thing when you turn the right change. So like even if there's one. Okay, is there any, so how many people are kind of done or completely done? Kind of done over there? Kind of done? Kind of done or, okay. So,
It's so much better.
so, by the way, there's an unavoidable like artistic quality to this thing because we could all have the same thing, but the way you lay out this thing could make it understandable versus not. So these are the states that I had, and I think I'm going to need a couple of extra to return to. Yeah. So, do you accept? Do you agree with this? So,
Because he knows what's up.
do you see? That's good, right? Like basically, you could have a pocket full of nickels and you get your whatever this thing is selling. But then from the initial state, you also can do this dime, and then the verticals are dimes also.
You even buy it for like one singular cheese.
Yeah. Anything else? Like I know that I'm forgetting one coin. Yeah.
The quarters.
So the quarter will actually, if I just put a quarter instantly, I get here. And then what else?
For like 5, 10.
So everything that is like at most 15, a quarter will be beneficial. So I could have like, so we're going to 40. Like so 5, that's going to take me to 30. So 10 is going to take me to 35. That's a quarter also. And 15 will take me to 40. By the way, this is our final state. That's actually the accepting state, yeah. Now, you can kind of see, like, I'll add one more, or is that it?
Don't you need to, like, what if we add a quarter if you have 20 cents already?
Yeah, so that's the question that Jade was asking. Now, the rest of it is actually, so if you have gotten to this point, I think that you've really gotten the gist of finite state machines. Then there's the issue of what do you do with the excess if they put in, which is what the question is. You can actually come up with, you're saying that as soon as this level is reached and exceeded, the machine stops taking coins. So then you could have a state for every potential overshooting state, like 1 for 45, and that state would also determine how much to be given back, right? So you could do that. In fact, all of those excess ones would also be in the finite state set. So like 45 would be double circle, 50 would be double circle, and so on. So, and then if I suspect everyone has something like this, right? Okay. The part that ends up being like, now that you know you have to give 30 cents, that interestingly connects to a warm-up question within algorithms, which is what's the fewest number of coins you could actually represent that amount? So in other words, like nobody wants 30 cents. Let's say 20 cents. Let's say that you were like at 35 cents, you were here, and then someone put a quarter in, so that became what, 60 cents. So you have to return 20 cents. Now, ideally you should do that with 2 dimes, but the machine could give you 4 nickels and you would not be so happy about that. You actually want to have like the fewest number. What would be the way to do that algorithmically speaking?
Would you just have another finite state machine to handle that?
I could do that. Can you tell me the logic that a normal human would go through to figure out the fewest number of coins that represent it?
You would probably take, so first you would see like the biggest, like take the biggest coin out of it and see if, like, so I would subtract 25 from 40.
Yeah.
And then the remainder would be
15.
15.
Mm-hmm.
And you would check, okay, that's less than 25, so then you would go to the next biggest coin, which is a dime, so 10, subtract that, and then all you're left with is 5 because we're not handling pennies, so
Yeah.
that's how.
Yeah, beautiful. Look, you would actually have this so-called greedy way of thinking about this. What's the largest coin that I could fit into the remaining amount? and I'll use as many of those as possible till I can no longer use one. At that point, maybe there's nothing left more to pay, or maybe there's some amount that cannot be represented by that coin. You go to the next smaller coin. That ends up becoming an example of what we call greedy algorithms, right? So this stupid vending machine actually is computer science all over it. So if you're okay with this, I feel like we have gotten to the point that I wanted this class to get to in terms of finite state machines, and there's a non-deterministic version of it, which I want to transition to, okay? Does anyone have any questions about this? All good? Okay. So just for sanity though, so what is Q here? Because I'm gonna ask you actually these things on the next exam. So like, what is the Q for this? Yeah, Lynn?
0, 5, 10, 15, 20, 25, 30, 35, 40.
And I'll take the time to write it because I think that sometimes I'm too sloppy here. And then there might be some extra space that we didn't bother putting in it, yeah. And what is sigma? Someone else? Yeah.
NDQ.
N, D, and Q. Okay. And what's little q? Someone? Yeah, what's little q?
40?
No. You said 40, right?
Yeah.
Uh,
It would be a 0?
yeah, 0. And remember, look, by the way, little q is an element of big Q. It must be one of the states. Yeah. Let's go for the easy ones, and then I'll focus on this one. What's F? Yeah.
40.
40, and then whatever extra things we could have added here to represent change. Yeah. What about the delta function? Is that a hand? Oh, okay. Anyone? What's the delta function? Remember that your answer should actually have a Cartesian product in it. No takers on this? Yeah.
Transition.
Yes, that's the transition logic, but can you tell me, like, mathematically speaking, how do I formally represent where it's going from, where it's going to, that transition function? Okay. So this is going to be a visual that I'm going to do for the first time, but I think it's going to be helpful for you. So what I'm going to do is I'm going to put the Q states here. So this is 0, this is 5, this is 10, 15, 20, 25, 30, 35, and 40. I won't worry about the change things right now to make it manageable. So this is my set of states. Now I have the 3 input symbols, so it could be a nickel, dime, and a quarter. It's a little Q, quarter. And then the way I personally suggested you guys think about is, blue, is that you always think about, like, what are the intersecting lines that I create by doing this? How do I intersect the points? Okay, so that actually creates the following elements to the Cartesian product. How many of those do I have? I have, like, so 2, 3, 4, 5, 6, 7, 8, 9 by 3, 27. I have 27 elements in the domain of this transition function. In fact, what I'm going to say is this right here is the domain of the delta function. Right, so do you see how the Cartesian product idea actually is now useful? It's formalizing what is this transition function taking as an input. Now, if this is a function, and I said it's a transition function, it needs to have a target. And the target will be given a particular state and a letter that makes you determine where you're going. But notice that the target doesn't have a coin associated with it. It's the current amount. So the target doesn't have a Cartesian product. The target is simply the amounts. So 0, 5, 10, 15, 20, 25, 30, 35, and 40. And let's just do 2 of them. So for instance, if I'm at 15 and I get a nickel, I go to 20. So if I'm at 15 and I get a nickel, I go to 20. And I can do this for all of those. Yeah.
So with what is that, delta?
Delta function, yeah.
Would the delta be from qx sigma
Excellent.
to
Q times, right? Like the Cartesian product?
Yeah.
Yeah. The sigma. So basically the Cartesian product of the states and the input symbols, that's the domain type, and it takes you to
q.
Q. Right? Yeah.
We ever define like the function, like what actually it's doing, like colon, and then like define.
Oh, okay, that's good. Like that was going to be literally my question. So this basically tells you the flavor of a function that I have. Like what kind of a domain does it expect? What kind of a target does it go to? But then it doesn't tell me what the function is really doing. And you know what the answer is? The answer is this. The finite state machine is the transition function.
Oh,
Yeah, so you could patiently write all these things, or I could patiently write all these arrows, but the finite state machine is actually the transition function, which captures whatever state that you want to have in your system. So in user interface design, a particular input, and then you click the submit button, but there could be like an extra character problem or an unknown username problem, right? That behavior about how events can unfold is a finite state machine. In a game, when I don't play games like you, I'm sure that you think about like how they come up, but check this out. This is a paper that I published with students of mine, and this was a while ago, but so sustainability themed problem solving in data structures algorithms, and in this case, this was more than 10 years ago. What I ended up doing was, do you know what the cod fish is, like its significance? Yeah.
Yeah, it's, oh, my brain just went blank.
It's an Atlantic fish.
Yeah.
And why do we tend to know about it more than other fish?
Because it helps to basically maintain healthy ecosystems.
Very nice. That I actually did not know, but the reason I know about it is that it was a main source of nutrition for many countries. Overhunting made it almost disappear. And this could have been devastating for like basically the Atlantic rim. So we wanted to model this in algorithms in COM 311. And this right here is the life cycle of a codfish. It doesn't exist. It exists, it's premature. If it actually just something happens, it could go to the dead state. It actually reaches maturity. At this point, it can reproduce. It mates, goes back to this seasonally, mates back, and at some point it dies. You basically have a finite state machine represent the state of a fish, and then you do a simulation of millions of these things, and you simply change the likelihood of this happening because of overfishing, and then you see that it actually just the population basically, look, just diminishes. So if you don't overfish, then it actually reaches sustainability like you see over here. So in this example, we were actually using algorithms to address a sustainability theme thing, and we were replicating what happened, almost happened in the Atlantic, but at the heart of this system, this experiment we did, the fish was represented as a finite state machine. So they are remarkably useful. They come up in all sorts of things. Okay, so 15 minutes is perfect, okay. Now, I want to go back to this. And do you guys have a red somewhere that you can toss me? There's no red? Doesn't matter, okay, that's okay. So this is right here, is a function. And what that means is these arrows, always, there's only one of them for each intersection. What if you permit two or more? What if I was actually allowed to take this point to multiple states? Then basically I'm saying if it's a function, it's a deterministic finite state machine. But if it's a relation, it's non-deterministic. Finite state machine. And the bottom line is, because this is not a formal grammars and automata class, like I can't have you engineer this or manufacture this knowledge in a month. The bottom line is this. These end up appearing to be more capable in expressing the state of a machine. The relation actually is powerful. It turns out that every single finite state machine that has a relation can be converted into a deterministic one. So I'm going to give you an example of it. I'm going to ask you like what you think is happening. So I have a particular example here. So can actually someone echo back what I said? What's non-determinism versus determinism in a finite state machine? Yeah.
Determinism is when you have one point to multiple outputs, but non-determinism is when it's only one point to one output. And then you can turn a non-deterministic function into a deterministic.
That's right. So the non-determinism could actually be helpful in capture the state of something you're interested in, but then that doesn't mean that it's more difficult. There's a process, there's an algorithm that turns it into a deterministic version. Can anyone guess how the change is going to affect the finite state machine? This would be a tall order. Like if one of you got it, like I'd be really, really impressed. So if I have a non-deterministic state machine, which means it's basically that, but the function is not a function, it's a relation. Then I turn it into a deterministic version. What do you think is the kind of change I could expect in my state machine?
I don't know if this is what you're looking for, but it'd be like a collection of functions. So like, you would have like two functions that would happen under two different conditions. It's like one of the arrows pointing to two places.
So can you, that was different than what I was looking for,
Okay.
but let me ask you a question. How many states do I have here without the chain stuff?
9.
9. Suppose that this was non-deterministic, and I do something to make it deterministic. Can you make a prediction about the number of states that machine is going to have?
Oh, I guess the maximum would be 9, either 2 9 or 9 squared. I can't.
It is, so you're right in the sense that it's going to have many more states,
Yeah.
but the rate of growth will be way worse than what you just said.
Okay.
And it's going to relate to power sets.
Oh, that makes sense. Okay.
Yeah. So let me draw one to you, and you tell me what this thing is doing. Good old-fashioned human-produced example. Sorry. China is really actually good at applying generative AI for customized learning, so I do understand the potential. It's just that we still matter, and we have to remember that. So this is 2, this is 0, this is 3, this is 4, this is 5. So this is A, B, and then A. I'm going to actually let you guys go early because I think I just realized this has something that, no, let's just do this. Let's just say A here. Yeah, that's good. And then this is A, this is A, this is A, and this is B. Okay, so the starting state is this one, and the final state is this. No, I messed this up, so it comes to A, this is 3. A spins here, it's the final states. This would be 4, and that's 5. So 3 goes to 4 with an A. There's none of this. And then 5, yeah. Can anyone characterize this, what this thing is doing? Or maybe I should say, where's the non-determinism? Yeah.
0 can either go to 1 or like -3.
That's right. So 0 is a state, and if A happens, you could be here or you could be happening here. So this, okay, so this is a problem because I cannot apply what I've known so far. But so why would this be useful? You're designing a game. Again, I'm going to venture into a space I don't know anything about, right? So like there's a character in there and some explosion takes place. That thing could be scared, or that thing could be called to arms. Same input, but you could go to 2 different states. So this actually non-determinism allows me to capture that. But ultimately, I want to have a functional version of this so that I can actually do something with it. So this right here, this one and this one, non-determinism. And I've said this before, maybe this is a good moment for me to repeat this. Human languages are non-deterministic, and that leads to ambiguity. So I could say one sentence and it could be very context specific. And that ambiguity, that non-determinism of what it means, is primarily the source of good literature. That's why poetry is so awesome sometimes, because of that ambiguity. Programming languages are not allowed to be non-deterministic. Otherwise, what you write, the machine could interpret it in different ways. So you write a program, Monday, Wednesday, Friday, it does one thing, Tuesday, Thursday, it does something else because of how it feels, right? That would be a non-deterministic machine, unacceptable, right? So this allows you to actually classify languages. So this non-determinism is the ambiguity part. Now, can you actually propose a way to turn it into a deterministic version? This would be, again, a tall order, but I still want to ask you, it's a good group. Not you. Yeah.
If you could remove the circular relationships.
You mean the
like-
double circles? Or when you say what do you mean? Oh, you mean like coming back to where you are?
Yeah.
Okay.
Yeah.
Interesting. Continue.
So if you could make it kind of like the other machine where you can only go in one direction instead of being able to go back to other states. So you stay in one direction.
I can have circular things in my deterministic versions also. So in other words, I don't see that as the enemy here. I think the enemy is that I don't know what to do here, because if A happens, like, where do I go? This, yeah.
Change one of the two A's that go out of 0 to B.
Say that again?
Change one of the two A's that go out of 0 to B.
To a B. But then the thing is, like, I could have situations like this, but you're getting closer. It's not the right answer, but you're getting closer. So if I'm here, and A takes me here, and A takes me here, and if I could be here, and B takes me here, and B takes me here, and B takes me here, and A takes me here, I could have combinations of these non-determinisms so that I can't just create a state. I could create worse versions of this because of multiple stages of ambiguity. Yeah, Chaz?
Could you have it point to one state, and then that state points to two states with different inputs?
Okay, so you might have the right idea.
It's kind of, so 0 would point to like another state called like 6, and then 6 would point to 1 or 2.
Nice.
That's really,
Okay, so this is what I'm going to do. I'm going to say, if I'm at state 0, then what's the alphabet here? A and B, right? If I get an A, I do something which I'm going to write here. If I get a B, I do something else which I write here. So if I'm at 0, I get an A. I could be in 1 or 3, right? I'm going to consider that a set of places that I could be. So non-determinism not taking you to a state, it's taking you to a set of states, and you could be at any one of them. And if I get a B, I don't actually have anything to do with B. So well, let's just do this. I won't finish this, so I don't know what the ramifications of that, but I just want to make it complete, right? Then I also want to do 1. So 1, if I get an A, I go to 2. B, there's nothing. So let's just say that 1 goes back to 1 with a B. Okay, and then I want to focus on 3. What does 3 do? 3 gets an A, goes back to itself. And it gets a B, it goes to 5. Check this out. Now I can actually address about this one. If I'm at this so-called made-up state of 1, 3, the places that it goes will be the union of the 1 and the 3 rows. So it says, if you were in this made-up state that where you could be either at 1 or 3, then if you get an A, you could be at 2 or 3, or you could be at 1 and 5. And then I would take these and expand them. But think about what's going on. I could have as many rows here as the number of subsets you could have of the set, and it's very explosive. So it's way worse than what you said. But the thing is, it's a finite number, right? If I have 10 things, 10 states, and there's massive amounts of non-determinism, as I turn it into a deterministic version, I will have up to 2 to the 10 new states, which is 10,024. So you go from 10 states with non-determinism to 1,000 states with determinism, and it's the exact same language. So what people do is they use non-determinism to conveniently capture a system in finite state machine version, and then they apply this algorithm to turn it into a deterministic version so that they can actually turn it into code. Right? This was a good class. I love this kind of stuff. And the fact that none of you are yawning right now, and this is like hardcore computer science, that makes me extremely happy today. So like I promised, Toby's going to get back to me with some examples from game design and user interface design. So we might actually tackle them tomorrow. So tomorrow will be the last day on this topic. And then next week we'll resume with counting, which was the regular schedule for this class. Yeah. All right, guys. Also, so yeah, one more photo, because I'm not going to do this for the quiz. I'm actually tracking like points and